Hello friends, we will in this experiment we want to implementation of a non-binary sequence counter using a finite state machine on an FPGA. So this is our some sequence, non-binary sequence. We want to implement that counter on an FPGA. So here if you see the sequence is 0, then 2, then 3, then 5, 6, 7, and then again 0, and it will should repeat at every clock edge. Right? So it should change the state at every clock positive edge of the clock, and it should go in this fashion. So here we can see there is no any relations from the present state to the next state. We can say it not an addition of one. We can find the present state to next state. It is applicable for all the state. There is no any mathematical relations to go up from the present state to next state. See here it is a non-binary sequence count. So for that we need to use a finite state machine. Finite state machine. Using the state diagram we can design this non-binary sequence counter. So here we need to display a different six state. So we require a six state diagram. Let's say to display the 0 we'll give this name of the state as s of 0, and we want to change the state from s of 0 to s of 1 at the positive edge of the clock, and we want to go from s of 0 to s of 2. In this s of 2 means we want to display the 2 when in a state 2. From s of 2 to s of 3 it displays the 3, then it goes into the s of 5, it will display the 5 from 2 to 5, then s of 6 and s of 7, and again start repeating with the s of 0. So we want to design the systems state diagram on an FPGA. So at every positive edge of clock it should change the state from one state to the next state. So this state diagram we want to implement on an FPGA. So for that to check presently the signal it is in which state, right? So we need to be defined some symbol. So it is called a user defined data types that we need to be defined on an VHDL. We can't check S0. We can check the 0 bit, we can check the 1 bit, we can check the 0 0, we can check 1 1, we can check the binary data, but we can't check any symbol, right? It is not in a STD underscore logic. So if we define any signal as an XTD underscore logic, we can check as an high impedance, we can check don't care, we can check strong 0, strong 1, weak 0, weak 1, but we can't check any state like any symbol as 0. So for that we need to be defined a user defined data types, right? So and then using the case statements at every positive edge of clock. So we'll check at every positive edge of clock we want to change the state, right? So we'll see at every positive edge of the clock it will change the state. If it's in a present state S0 it will go to the S2. If the present state is S2 it will go in S3. If the present state is S3 it will go in S5, like that, right? So depending on the present state it will be next state will be the derived. So to check the positive edge of the clock, what should be the syntax in a checking condition in a VHDL is clock event and clock equal to 1, ending with clock equal to 1. It will check the positive edge of the clock, right? Then what we have to do, then first of all we have to check what is the present state, and according that we have to take the decisions, right? So we have to use the cache, and cache as is, where s is one of the either S0 to S7. It is signal S, which is type stat, right? So we have to check in a case S. If the S is in S0, then we will display in output output is 0, and it will move in the next state. It is S2. So let's see what is the VHDL code for this. What should be the VHDL code? So here we can see the VHDL code for the non-binary sequence counter using the FSMs. Using the FSMs. So let me implement using the FPGA. So first step is to close all the previous project. Then new VHDL, and this is the program for VHDL code for non-binary sequence counter using FSM, finite state machines, using FSM. So here let's see, first is the library and the packet declaration. So library is IEEE and package is std_logic_116. Then the entity and name, let's give the non-binary counter is port. What are the ports for the non-binary counter? So we know the counter have only one input, clock, and if we have some reset signal, then we can have the two input, clock and the reset. So this counter also have the clock and the reset inputs in std_logic, and X is the output, non-binary output for 0 to 7. So for that range is integer range 0 to 8. Then and entity name. So this is simple entity declarations of a non-binary sequence counter. Next step is to the architecture body. So architecture, name of architecture, here the given name of architecture is simple_FSM of entity name. So this is the entity name, non-binary counter is. Now, as I told, need to be defined a user-defined data types. So syntax to define a user-defined data types in a VHDL is type, any new type you want to define, then type. This type is type of stat is. Now stat can understand what stat can understand the different symbols. So stat can understand S0, S2, S3, S5, S6 and S7. So we can assign to stat any symbol value, either S0, S2, S3, S5, S6 and S7. Like suppose if we define the signal as a std_logic, then as we can assign a strong 0, strong 1, weak 0, weak 1, don't care, high impedance, like that. In here we have defined a new user-defined types. It is a stat, and in that stat we can assign a different symbols. Now let's define a signal as type of stat. So in the S we can assign it any value S0 to S7, S0, S2, S3, S5, S6 and S7 in S. Then the begin, here it is implementation using the behavior architecture modeling. So in the process statement, and inside the process statement as sensitivity list, when we want to run the code which is written between the begin and end process, that we have to write inside the sensitivity list. So as a sensitivity is normally all the inputs, it is in the sensitivity list. Then the begin, now whatever you write the after begin, all the syntax run the sequence. It is run the one by one in the sequence. So first step is we have to check reset is equal to 1. If the reset is equal to 1, then it will assign stat initialized with the S0. So we'll assign it as S0. Else means stat reset is equal to 0. Then we'll check if have any clock edged or not. Right. So if else clock event and clock equal to 1, then we have to check what is the present state, and accordingly we have to according that we have to transfer in output, and as well as we have to change the state. So here we have used the case statements. So case S is, now it will check what is the value of S. Suppose the present value of S is S0. So when S0, then what the task we want to perform, equal less than that indicate what the task we want to perform. So if the S it is S0 means the present in a S0 state, then it will perform, it will transfer in output 0 and it will change the state, new state value will be the S2. So again at the next positive edge of the clock, it will check what is the value of S. So now at that time value of S will be the S2. So it will go to in this state, in this when statements, when S2, then it will perform transfer in output A2 and it will change the state from S2 to S3. It will assign the S to the new state S3. Right, and again at the next positive edge of the clock, what will be the value of S? It will be the S3, so it will perform this task, right? And according that, according the present state, it's have the perform different tasks. So when it is in a S7, at that times, when it is in a S7, it will assign as x is equal to 7 and the present state now again S0. So it will repeat start with the S0. When others means other than this combination, other than the conditions of the case, it will assign to null. AND case, end of if and then the end for the process and the end for the architecture. So this is the simple program using the FSM to implement a non-binary sequence counter. So next step is to save this file. Let me save this file. Let create one folder, experiment number, let's say 7. Let's save this file with the entity name. So here we have to select the device, it is Cyclone 2 and device is, this is the device 484C7. Next, and finish. Now we have to, next task is to compile the design. So let me compile this design. So compilation will take some time to compile the design. So here we can see the compilation summary reports. Next task is to, if you want to implement our design on an FPGA board, next task is to go to assignments. And let me first see the output in a vector reform file. So for that we have to go in a new vector reform file, and here we have to insert the node and bus. So here we can see the node and bus. So let me give first input is let's say reset for, so it will initialize with the S0 state and clock, let's assign the clock, right? And let's save this file. Next task is to perform functional simulations. Let's do the settings for the functional simulation. Simulator settings, and then after the setting of as a functional simulation, for that we need to generate one extra file. It is called a generate functional simulation netlist file. Click on it, it start generate a functional simulation netlist file. After that do the simulations. So here we can see our outputs, right? So here we can see the outputs when the reset is equal to 1 and the clock is positive as it is in a S0 state, and in S0 state output is 0. At the next positive edge, you can see the reset is equal to 0 and positive edge, so it will be the present state is S0, it is in S0 state. At next positive edge, it goes from S0 to S2 state, then S3, then S5, 5, 6, 7, and again repeat from 0, 2, 3, 5, 6, and 7. So here we will get the output. It is as per our design, whatever we want to display. So output is a non-binary sequence output. So similar, if you want to implement on an FPGA board, task is to do the pins planner. So once in pin planner, here we require the two input pins. We can use any two switch as an inputs. So for the switch, let's see what is the pin number of switch. So let me use S0 for the switch for the reset and SW1 for the clock. So L22 it is for reset. So for reset we use L22 and L21 we use as a clock. Okay. So our first pin is reset and second pin it is a clock. Now we require the four outputs. So for output, let's see the four output on an LED. So we'll use the 4 pins of LED. Here also we can copy this, and here we can select the 4 and we can test it. Once we assign the pin planner, next task is to do again the full comparison. So let's do again the full comparisons before implementation on an FPGA chip. Next task is to implement the SR programming file on an FPGA. Go to the tools, programmer. So here the .sf file of non-binary counter is already included in this, and program and configuration, and start the program. So here in this board, once it's programmed, the blink, automatic blinking will be the off, and later on it work as our desired functions. Right. So these are the 4 switch we have used. These are the 2 switch. First switch we have used for the reset. So let me keep first the reset is equal to 1, right? And this is our clock. Let me give the clock. So our output is the state is 0. So 0, this 4 LED we have used to see the output. So first LED, this is the LSB, and this one LED is the MSB bits, right? So this 4 bits output. Then let give the reset is equal to 0, and let me give the clock the positive edge. So this is the output 2. Then this output is equal to this is output 6. So for which the different state we have designed, we get different outputs. Here we can see the result. Here our output in a binary, and it is in a LED display of LED. If you want to see our output on a 7-segment display, output